We'll cover these specific topics: instrument altitudes, en route low altitude charts, holding procedures, estimating time en route, and fuel consumption. Okay, let's tackle our first topic in this lesson: IFR altitudes. Join your instructor in the classroom for that topic.
It's time to study IFR altitudes. Since IFR flight is conducted without reference to the terrain, the FAA prescribes certain altitudes. These altitudes depend on a number of factors such as the topography, navigation signal reception, and other aspects. We'll start with 5 different instrument altitude types. Now, 4 of them are minimum altitudes, and 1 is actually a maximum altitude. The 4 minimum altitudes are first MEA, or minimum en route altitude, MOCA, or minimum obstruction clearance altitude, MRA, or minimum reception altitude, MAA, or maximum authorized altitude, and finally MCA, or minimum crossing altitude. Now, all of these altitudes provide us with a minimum obstruction clearance of 1,000 feet or 2,000 feet in mountainous areas. You distinguish mountainous areas with this chart provided by the FAA showing mountainous areas here. Notice the entire western United States is actually considered mountainous area, shown with this shading. In the eastern U.S., the Appalachian Mountains are the only areas that are covered with a similar gray shaded area. Let's focus on the first of our minimum altitudes, the MEA, or the minimum en route altitude. Now, the MEA is the lowest en route altitude to receive a satisfactory signal along airways called Victor Airways in our system. An airway is represented by this line that you see right here. This shaded rectangle contains the name of the route, such as Victor 267 or Victor 480. Now, above the rectangular shaded box is the flight segment minimum en route altitude. You can see that right here. When only one altitude is shown, that altitude applies in both directions along the airway. If there is only one MEA for the route segment, it is shown as a single number. Now, below the box, the length of the segment is shown in nautical miles. The MEA guarantees navigational coverage at that altitude, but does not guarantee communication coverage. So be aware, in some areas of the country, you may have navigational coverage at the MEA, but no communication coverage. Now, here's another altitude. This one is the MOCA. No, I don't mean a fancy caffeinated beverage, but the MOCA stands for the minimum obstruction clearance altitude. Now, a MOCA is often co-located with an MEA and shown here with an asterisk, and you can see that right down here. The MOCA provides obstruction clearance, but does not guarantee radio coverage unless you are within 22 nautical miles of a VOR. MOCAs are used in emergencies when you encounter in-flight icing, as an example, and need a lower altitude. The MOCA gives you a safe option to descend and continue at a lower level, knowing you are still safely above en route obstacles. When aircraft must be at different altitudes to guarantee radio reception, a minimum reception altitude, or MRA, is used. An MRA is shown with this flag that you see right here. The MRA guarantees the pilot can receive an off-airway navigational signal. Now, here's another altitude. This one is the MCA, or the minimum crossing altitude. Now, MCAs are shown with an X in a particular flag, and you see one located right down here. The MCA is a minimum altitude for crossing a navigational aid. There is crossing information attached to the MCA above the nav aid data block, like we see right here. The MCA shows the airway involved, the direction of flight, and the altitude to fly. You have to plan ahead for an MCA so you are at the proper altitude before crossing the nav aid. MCAs may be required for obstruction clearance or because of reception requirements. You must comply with any MCAs you encounter in flight. Now, here's an MAA, which means a maximum authorized altitude. MAAs show maximum flight altitudes for receiving an adequate navigational signal. There are not a lot of them in the country, and it's unlikely you'll ever need to use an MAA in a typical general aviation aircraft, but you may encounter one or two in your flight travels, and you need to know about them.
Welcome back. Let's take on some questions here and review. If no MCA is specified, what is the lowest altitude for crossing a radio fix beyond which a higher minimum applies. Which is true? Well, your correct answer is A. If a normal climb commenced immediately after passing a fix beyond which a higher MEA applies would not assure adequate obstruction clearance, then a MCA is specified. Otherwise, cross the radio fix at the MEA at which it is approached and then climb to the next higher MEA. Answer again, A. All right, another question. Acceptable navigational signal coverage at the MOCA is assured for a distance from the VOR of only what distance in nautical miles? Well, your correct answer here is B, 22 nautical miles. Minimum obstruction clearance altitude, or MOCA, is the lowest published altitude in effect between radio fixes on VOR airways, off-airway routes, or route segments, which meets obstacle clearance requirements for the entire route segment, and which assures acceptable navigational signal coverage only within 25 statute or 22 nautical miles of a VOR. Okay, and our third question. Reception of signals from an off-airway radio facility may be inadequate to identify the fix at the designated MEA. In this case, which altitude is designated for the fix? A, B, or C? Correct answer, A. MRA, or minimum reception altitude, is the lowest altitude required to receive adequate signals to determine specific fixes. Reception of signals from a radio facility located off the airway being flown may be inadequate at the designated MEA, in which case an MRA is designated for the fix. Okay, let's take a look at another topic. Enroute charts. Join your instructor in the classroom for that one.
Let's go over the Enroute charts. IFR Enroute charts are a key component for the operation in the instrument environment. They provide the information you need to navigate, select altitudes, communicate, and plan your flight. Here's an example of an Enroute chart here. Notice it looks strikingly different compared to a VFR chart that you already know. They seem to have much less information on them. In fact, they contain almost no topographical information whatsoever, since there's really no need to see rivers, roads, cities, coastlines, and any of that sort of information, although the wise pilot will always carry a VFR chart for any route of flight as part of your careful flight planning. Now, they do have a lot of codified information to help you fly safely in instrument conditions, so let's learn some new chart information now. Low altitude Enroute charts are valid up to, but not including, 18,000 feet. For flight above 18,000 feet, there is a separate set of high altitude Enroute charts. Please note the symbols we will be discussing and using here are for the U.S. government NACO charts. Now, other commercially available charts may use slightly different symbols, but the test questions you will encounter will all use the U.S. government symbols that we will cover here. Let's take a look at some of these charts now.
We are very pleased to have Barry Schiff with us in the studio today. Let me give you a little background on Barry. He has more than 27,000 hours of flying and more than 300 different aircraft. He has received worldwide recognition for a wide range of accomplishments, including being an airline transport pilot at the age of 21. He's earned nearly every FAA category, class, and instructor rating. And during his 34-year career with Trans World Airlines, he flew everything from the Lockheed Constellation to the Boeing 747, and he was check captain on the Boeing 767. Captain Schiff holds 5 world speed records and has received numerous honors for his many contributions to aviation safety. An award-winning journalist and author, he's well known to flying audiences worldwide for his numerous books and almost 1,400 published articles. These credentials have not diminished his passion for flying light aircraft, however, which he has used to span oceans and continents. Now, he continues to investigate and report to the aviation community various aspects of proficiency and safety and remains a vigorous and outspoken advocate for general aviation. Barry, welcome.
Thank you very much. I think it's terribly important that pilots remain familiar with their navigational charts, sectional charts. I love to fly along and pinpoint my position using my fingers on the chart and keeping track of exactly where I am. Not only do you remain proficient at that kind of very basic navigation in case the electrical system fails and you can't use GPS, but it also provides a great deal of satisfaction that you can fly the basic way. I suppose if one can say if man were intended to navigate, he would do it with his eyes, and I prefer doing it that way. I love to fly topographically.
During your knowledge exam, you do not actually receive entire sets of charts for test use. You will receive sections for individual questions and problems. You also receive legends for those chart sections, like the one that we see right here. Now, I recommend looking at the legends ahead of time. Familiarize yourself with the legend information and the symbols for different functions. Also, use these as a resource during your test, since they will be available to you as part of the computer testing supplement you're handed at the testing center. What symbols are on an IFR Enroute chart? Let's look closely at a chart legend here. Here are some symbols relating to airports. In this particular section, they're divided into land and sea airports. Blue and green symbols show airports with an approved approach, and airports in brown indicate an airport without an approved approach procedure. Color coding lets you see very quickly which airports have an approved approach. Now here we see the data block that provides the information about the runway length, the elevation, and other critical information. Let's look more closely at each component. Reading across the top, we see that the airport name is shown right up here. A small box with a D or C next to the name indicates Class C or Class D airspace at this particular location. The second line shows airport elevation, and then an L will be shown if airport lighting is available, or a dash if lighting is not available. A star symbol next to lighting indicates that the lighting is available part-time or upon request. After lighting, we have the length of the longest runway in hundreds of feet. On the third line, an A indicates the availability of automatic terminal information service, and if it is followed by a star, then the star indicates that the service is only part-time. Last is the frequency for contacting the automatic information system. Another section of the legend shows us information about nav aids such as VORs and NDBs. Now, 4 icons represent nav aids providing radial and in some cases radial and distance information for military and civilian use. These 4 are Vortechs, VORs, VOR DMEs, and TACANs. Now there are also 4 non-directional locator beacons, or NDBs, and you see those shown right here. These nav aids have a small arrow barb pointing at magnetic north. Here's an example right here. The black symbols represent very high or ultra-high frequency nav aids, and the brown symbols represent low or medium frequency nav aids. Here's another little symbol. This circle dot represents a flight service station, remote communications outlet, which is called an RCO. You see that right here. Another symbol is this localizer barb that we see down here. And the localizer barb with an additional navigation function, such as one shown right here, will be shown on an Enroute chart. In this enlargement, we can see very clearly the value of the barb protruding from the nav aid. And you can see in this slide how the barb orientates on the compass to magnetic north, providing another clue to help with headings and courses in flight. Another part of the legend box shows the data blocks. Here's an example right here. And these accompany the nav aids. Now, if you see a VOR frequency with a line underneath it, it means voice capability is not transferred over that frequency. Frequencies without lines underneath mean that you can transmit voice over that frequency. The frequency at the top left of the box is used to communicate with flight service, and the one over here to the right with the R shows that a frequency you can use to receive voice from the flight service station. Now, a box with a shadow signifies that there is a flight service station associated with that particular VOR. Sometimes you may see a data block like this one right here showing a name in brackets beneath the data block. Now, this is an RCO, or remote communications outlet. We mentioned a moment ago how RCOs look like circle dots on the chart. RCOs are used to remotely communicate with the flight service station through a separate location. The name in brackets is the name of the actual remote location of the flight service station and not the location of the facility you are using. For your FAA knowledge exam, when you are asked about frequencies, Remember that the 121.5 frequency, the emergency frequency, is monitored everywhere, so it is not displayed above these information boxes. Let's look at a communication box associated with a flight service station like this example here. Now the frequency for two-way communication with the flight service station will be shown here and first in line like this example shows here. Now you may also see another frequency with an R next to it. This means receive, and it is most often seen in remote areas. It simply means that your voice can be broadcast to the flight service station on the regular frequency, but you can tune up the R frequency on your second radio to receive the flight service station reply, amplified through the nav aid. Let's take a look at these symbols on an actual low altitude en route chart. Here's an example of a flight service station shown right here as the Denver Flight Service Station. Now here we see the Corvallis VOR DME. Now the chart shows the VOR DME symbol right here in the middle. Over here to the left we see the data box. Now over here is the ILS localizer symbol for McNary Field, showing an ILS being used for navigational purposes. Let's take a look at some more symbols. Here we show a Vortech, which is a combined VOR and TACAN. You can see that right in the middle. It looks a lot different than a VOR DME. And here we show an NDB, which is easy to distinguish on this chart with its different color, its distinctive dot pattern, and the barb pointing to magnetic north. Now that's a good segue to our next slide. Here we look at three ways symbols are used on a nav aid. First, magnetic north is also indicated with a similar barb to the one that we just saw. The black line here shows how en route airways radiate from VORs and are always darker bold lines. And here we see the same VOR generating a radial, shown with this thinner line, being used to identify the location of an airway intersection. Now, federal low-altitude airways are 8 nautical miles wide or protected 4 miles in either direction from the center line. These airways are located at any altitude from a base altitude of 1,200 feet AGL up to 17,999 feet MSL, just short of 18,000 feet. These low-altitude airways have protected airspace all around them, as represented by this purple-colored graphic tube, which extends protection for the entire length of the airway. Now, high-altitude airways are also called jet routes, and they range from 18,000 feet MSL to 45,000 feet MSL, which is also known as flight level 450. Now, back to the chart legend. An airway is made of segments shown with these T-shaped markings that we see right here. Here's an example. And these are used to define when an airway meets an intersection, also called a fix, and it's indicated on charts with these little triangles that you see right here. A fix identifies a changing point, like an MEA change, after passing the fix. Now, traveling southeast along Victor 287, you see that right here, Camas intersection is identified in part by the intersection of the 210-degree radial. Notice how here the MEA is 8,000 feet with a direction indicating which way that altitude applies, and after Camas the MEA jumps to 8,500 feet. Now the MOCA also changes, jumping from 5,500 feet up here to 6,000 feet after Camas intersection. Now if you see this scenario on a route that you're flying, you want to start gaining altitude prior to crossing Camas so that you can be in compliance with the new route segment as you cross over. Now let's talk about distances on airways. Now distances are shown along each airway and are measured in nautical miles. While you're flying on an airway, you can directly read the distances. Now when you are off airways, use the scale provided on the bottom of the low altitude chart or a plotter made for IFR plotting. Now the VFR and WAC scales are different and will not work on IFR charts, so don't try and use your VFR plotter here. The chart legend covers distances over here in this section, and by enlarging this detail you can see the highlighted areas show mileage between reporting points, which is the numbers underneath an airway. And in this entire section it shows 4 ways that are differently used for tracking distances on a chart. Now let's go back to the chart and take a look. Distances are shown along the underside of an airway like this example right here. Back to the legend. We can see DME distances are shown with digits inside a D and an arrow pointing to the measurement. Let's put some of this knowledge to use on a chart. Look at Victor Airway 287 heading southeast. Here's our example again. If we add up the two segment distances of 12 and 22 nautical miles, we see that 12 plus 22 equals 34, which is also the same distance shown here with this DME box. Now, back to the legend. This time, we can look to see total mileages between the compulsory reporting points, or nav aids. We are still using Victor 287 as our example. Now, you can add up all the segment sections, 12 plus 22 plus 21 plus 7 plus 17 equals 79 miles, or you can just look here and you can see that the total distance is 79 nautical miles shown in this box. You already know that VOR signals weaken as you fly away from the nav aid and get stronger and more accurate as you fly towards the nav aid. So in IFR flight, how do you know when to switch VORs? Well, the chart makers provide a solution, and here's an example right here with this crossover symbol like the one we see. Let's take a look at this on an actual chart. For this example, look over here on Victor 23. You can see the symbol right here. This is a VOR changeover point. Now notice that the 40 miles shown here for the shorter segment combined with the 59 miles shown right here for the longer segment equals the 99 total miles right here. Now if there's no changeover point, simply switch your nav aids at the halfway point on the chart. Sometimes an airway has a dogleg turn, and when you see a dogleg, consider it to be the switchover point. Now let's go back to the legend, and this time let's look at boundaries. Now here in the legend close-up, you can see an interesting squiggly edged box right here. That denotes a frequency for air traffic control in the area you are flying. Now the name of the center and the frequency will be provided as we see right here in this particular box. It'd be right down here. Let's look on a chart and see if we can find a good example. Right below the data box for Mendocino VOR, we find this Air Route Control Center designation box. Here's an example right here. Oakland is the center name, and the bottom of the box we have our VHF and UHF frequencies. Let's go back to the legend again, this time for a closer look at compulsory and non-compulsory reporting points. Compulsory reporting points are shown like this here with a solid black triangle. Here's an example. And non-compulsory points are shown with an open or white triangle like we see right here. Now let's go back to the chart. Here's a compulsory reporting point shown with a black triangle right here. And you're flying over a Vortech, and it's actually co-located with the Vortech right inside the symbol. Now you must report 6 items: your position, the time in minutes past the hour, your altitude, the type of your flight plan, the ETA, and identification of your next reporting point, and the name of the next reporting point. Back to the chart, we can see an open triangle, non-compulsory reporting point here on this particular airway. Here's the example right up here. These are voluntary reporting unless radar contact is lost, and then you must treat them like a regular compulsory reporting point. However, if you are in radar contact, no report is required.
Welcome back to the studio. Let's review some of the information you just covered with a couple of questions. We're going to ask you to refer to a figure here in a moment. Where is the VOR changeover point on Victor 20 between Beaumont and Hobby? Well, let's take a look at our chart and see how we figure this out. First, we find Victor 20. That's located right there. Then we take a look at an overlay of the Beaumont Municipal Airport there. And here's Hobby, our destination. We plan our route of flight. And then we look at the VOR, and it should show that it's the midpoint. Let's take a look at our question again. That's true, the halfway point rather. Correct answer is A. All right, taking a look at another question. Referring to figures again, which Vortech along the proposed route of flight could provide HIWAS information? Which Vortech? So we have to look at our figures again to find out which of these Vortechs will apply HIWAS, provide us with HIWAS. Well, there's Kingston up here. We have our flight path. Zoom in on that Kingston. We see an H in the upper right-hand corner there that indicates HIWAS capability. So we go back to our question, which is it? C is the correct answer. The Kingston Vortech description contains the H, therefore it provides HIWAS information. All right, let's go to another topic. And we're going to holding procedures. Back into the classroom for that discussion.
Next are holding procedures. Occasionally, ATC is so busy sequencing airplanes for approach and landing that the only safe thing to do is wait your turn. In IFR flight, this is called holding, and the FAA recommends certain procedures to do this properly. Here's a typical IFR low altitude en route chart, and this little symbol is a holding pattern. You can see it right here. Let's look a little closer. It actually looks like a racetrack, doesn't it? Now it's true, you do go around in circles, but there are 4 very good reasons for doing so. These are the 4 primary reasons to hold. First could be weather delays, could be some traffic delays, to reverse course, or to lose altitude. Now a storm in front of you along your route could justify holding until the route is safer. ATC may ask you to hold, waiting for traffic in front to clear so that they can maintain safe aircraft spacing. You might need to use a hold to reverse course on an arrival to transition safely into an approach, and yet another use of a hold is to lose altitude. As an example, you've just crossed a ridge at a high and safe altitude on an airway, and now you must descend a transition to an arrival phase at a lower elevation airport. A hold is a great way to safely decrease altitude. So how do you hold? Let's talk about the different ways of handling a hold safely and smoothly. Now you may go months without needing to hold, but when ATC or a situation requires it, you must be able to do one without hesitation. You're also required to demonstrate a hold as part of the instrument currency requirements, so this procedure won't go away once your check ride is completed. This graphic shows how a hold appears on the chart, but flying it is actually a different matter. Now on the chart, for clarity, the hold may not always be touching the fix. In this graphic, the top illustration shows how a holding pattern may actually appear on a chart, while the bottom illustration shows how it is actually flown. In this case, you can see it's actually touching the fix, or a specific point identified by a nav aid or an intersection. And you can use any combination of VORs, NDBs, GPS waypoints, or DME distances to identify a point or fix for the hold. Now explaining this is going to require a more detailed graphic, so let's take a look at that here. Let's look at the components. This hold side is the protected side where you can safely turn within a guaranteed protected airspace. Now on the other side, it's unprotected, which is an important aspect to remember for safety. When this racetrack-shaped holding pattern is placed on the fix shown right here, the first place to look is here, the inbound leg. This would be our inbound leg. This is the leg where you will always be flying inbound to your holding fix. Now flying the inbound leg always provides a precise segment transition at the moment your instrument indicates you are passing over the fix. While the inbound leg is the most important, you also have to fly an outbound leg, which is shown right here. This will get you into position to fly the next inbound leg. Now you get to the outbound leg by crossing the fix at the abeam point, which is always an imaginary line drawn across the fix at the 90-degree angle that you see right here. You pass the fix or abeam point and immediately start turning at what the FAA calls the fix end of the pattern, yet most instructors will call this the outbound turn, since it is the turn that carries you into your outbound leg. Now at the other side of the racetrack is what the FAA calls the outbound turn, yet most instructors will call this the inbound turn, since you're actually turning in towards the inbound leg. So how do you actually fly a hold? Let's look at the holding format first, shown in this next slide. First, ATC will always give you several things in a hold clearance. First, a holding fix and a compass direction, a course radial or bearing, a direction of the turn, although right turns are standard unless otherwise specified, and an EFC or expect further clearance time. So if you lose radio communication while holding, you know how long to remain in the holding pattern. Now here's an example of an ATC holding instruction. Cessna 3236 Echo, hold west of Flugel intersection on the 185-degree radial, left turns, expect further clearance at 15 past the hour. Usually you will use a VOR bearing from the station to identify the hold, and they are most common, yet it's important to note that if an NDB bearing is used, the bearings are always measured to the station. Of course, if a hold is depicted on a chart, ATC may just simply issue a clearance to hold as published. Now with the clearance to hold, the first step is to actually fly to the fix. That's all you do first. Fly a straight line course using the course or bearing that takes you right to the fix. Your job in step 1 is just to get there. Now, step 2 is more interesting. You must determine the entry type to properly enter the racetrack holding pattern. Now, there are 3 recommended types of entries, each chosen to be the easiest and best way to enter a holding pattern, depending on the angle at which you are approaching the fix. Let's mask this chart down to the area related to the published hold and zoom in on the holding area. Now, let's start looking at all the individual components. The first is the Vortech itself, and the second is the radial given for the hold that terminates at the Vortech station. You can see that example shown right here. While the published hold is set to the side of the Vortech and radial for clarity, the actual holding pattern is on the holding radial, and the curve of the holding pattern starts right at the Vortech station. Now, to figure out which entry pattern to use, you start by drawing a line through the holding pattern at the fix that is 70 degrees to the holding radial. Any airplane approaching the fix in this shaded area would use a direct entry. Now, in a few minutes, we'll illustrate the entry paths, but for right now, let's focus on determining which entry type to use as you approach the station. Now, the smallest angle up here is the area for teardrop entries. That's shown right here. And the last area of the approach is defined by this segment right here, and that's actually defining when we would do a parallel entry. Now, we are ready for step 2. Let's look at how the aircraft actually flies across the fix in preparation for entering any of the 3 patterns. We'll start with direct. Anywhere in this largest shaded area, any approaching aircraft simply flies across the nav aid, and in this case, after station passage, will turn to the right and enter the hold. For teardrop entry, the aircraft crosses the fix and continues into the holding area at an angle. It's this shape, the teardrop shape, that forms as the aircraft starts the turn to the right to enter the pattern that gives the hold entry its name. The last entry is actually the parallel entry. As the aircraft crosses the fix, it must immediately turn and fly parallel to the inbound leg of the hold and continue until it is ready to begin turning into the holding side to intercept and track the holding radial inbound. Now, once the aircraft crosses the fix while flying inbound after completing the entry, the pilot turns the aircraft into the fix end and continues a 180-degree turn until established on the outbound leg that you see here. Now, after passing the abeam point, the pilot flies for 1 minute and then it starts a turn inbound towards the fix to track the leg back to the station to begin the hold again, or as long as that hold is necessary. Let's take a look at a hold one more time for clarity. Notice that as the aircraft crosses the fix, it begins the turn into the protected side of the hold until passing abeam the fix, at which point it travels outbound for 1 minute before turning inbound to intercept the inbound holding course and track to the fix. Now, here's the parallel entry. Let's take a look at actually flying a parallel entry. Now, as the plane crosses the fix from the parallel entry area, the pilot immediately turns and flies parallel to the inbound leg, flying away from the fix for 1 minute. At the end of the minute, the pilot turns into the protected hold area and continues a turn past 180 degrees to intercept the inbound leg. This first inbound leg will not be a minute long, but that is all right after the pilot crosses the station and begins flying the regular holding pattern. The inbound and outbound legs will begin averaging a minute for each leg, as you can see here now that the aircraft has entered the standard hold. Finally, let's check the teardrop entry out shown in this next graphic. Now, once the aircraft crosses the fix after entering from the teardrop entry area, the pilot continues to fly straight ahead for approximately a minute and then starts a turn towards the inbound leg, and after intercepting the inbound leg, continues around the holding pattern as long as required to hold. Now, there are airspeed limitations for holding patterns, and we'll look at them now. Below 6,000 feet, the limit is 200 knots. Between 6,000 feet and 14,000 feet, the limit is 230 knots, and above 14,000 feet, the speed limit is 265 knots. Now, most general aviation aircraft won't need to worry about the differences, but if you were to fly a jet aircraft and start holding at 14,000 feet and stayed in the hold to lose altitude, you might need to change airspeeds even while holding. Now, let's not hold off any longer. It's time for another FAA review question.
Okay, now we have a couple of additional questions for you in review. We're going to ask you to refer to a figure here in a second. At strut intersection headed eastbound, ATC instructs you to hold west on the 10 DME fix west of LCH on Victor 306. Standard turns. What entry procedure is recommended? Which of these three? Well, we look at our figure. We find strut. Okay, we go to this figure. We note that the aircraft is in the direct entry sector, flying on Victor 306. So we go back to our question, which is the correct answer? A. When eastbound, a direct entry is the recommended entry. Okay, our second question, again referring to some figures here. You received this ATC clearance. Hold west of the 15 DME fix on the 086 radial of ABC Vortech 5-mile legs left turns. You arrive at the 15 DME fix on a heading of 350 degrees. Which holding pattern correctly complies with these instructions, and what is the recommended procedure? Okay, well, we'll look at this figure here. We actually have two figures. One, holding pattern is north of the airway. Two, the holding pattern is south of the airway. This shows us that our aircraft flying at 350 degrees is in the direct entry sector. So, back to our question. So, answer C, choice 1, direct entry, is the correct answer. All right, let's move along to a new topic. This time out, time en route. Back to the classroom.
Next up is estimating time en route. Estimating time en route is a fundamental element the competent aviator should do well. However, when in IFR flight, it is even more important since only airports with instrument approach procedures may be available for a landing. Now, you can use either an E6B or an electronic calculator for the necessary calculations. There are really 5 variables to consider for these calculations, including calculating the magnetic heading, winds aloft, distance for each leg, ground speed for each leg, and completing the process with computing your time en route.
Now, Barry, do you have a rule of thumb for accounting for time differences when flying between time zones?
Oh, how I wish I did. I think crossing numerous time zones is the curse and bane of the pilot. When I used to fly around the world, once a month, once around the world, it was the best airline duty I ever had. It was an 11-day trip, but after about 5 days, you'd wind up in Bombay, India, where the clock was about 12 hours off of home time. And there was absolutely no way to compensate for time zone changes. I'm one of the worst victims of that syndrome, the time zone syndrome. I found that in India, I would go to bed hungry and sit down at the dinner table and fall asleep. I mean, there was just no way to synchronize my body with time zones when you cross them that rapidly. Even when you go from LA to New York or cross 1 or 2 time zones, it takes a certain amount of time to become adjusted. And the biggest secret about crossing time zones is that there is no secret. There is no way to compensate. You simply have to get to your destination and grin and bear the time zone change until you readapt. And in case you're wondering, it takes about 1 day for every hour of time zone change to adapt to a new time zone. For example, if you're going from LA to London, it's an 8-hour time zone change. I find it takes a week before you're fully acclimated to the new time zone.
Okay, let's look at this review question. Refer to the figure in a moment. Southbound on Victor 257, at what time should you arrive at DBS Vortech if you crossed over CPN Vortech at 0850 and over Divid intersection at 0854? Well, in order to arrive at this, we do have to look at our figures. Here's figure 91 from the FAA. Let's zoom in to the 2 points of interest, CPN Vortech at 0850, Divid at 0854. We see that at Divid, the 9 nautical miles in 4 minutes equals a ground speed of 135 knots. So now we have our ground speed. We go back and look at our planned flight at divot at 0854. We add 71 miles between DLN and DBS to the 39 miles remaining length prior to reaching DLN to get a distance of 110 nautical miles. Now, using the ground speed we established at 135 knots for a distance of 110 nautical miles, calculate your time of 48 minutes and 53 seconds, or you can round it up to 49 minutes. If the time was 0854 at divot intersection, 0854 plus 49 minutes equals 0943 at DBS. So, what's the correct answer? Of course, B. Time was 0854 at divot intersection. 0854 plus 49 minutes equals 0943. Okay, let's take a look at our final topic here in this lesson. Fuel consumption is the topic. Back to your classroom for the discussion.
This section covers fuel consumption. A primary skill the instrument pilot must master is estimating fuel consumption. Generally, if done correctly, you'll land with plenty of fuel, or if unable to land at the destination, there is plenty of fuel left to land at an alternate airport. Solving fuel consumption requires three components. First, calculating ground speed. Second, finding time en route. And calculating your total fuel used.
Do you think there's any life left in the E6B?
I would like to think there is. At least I hope there is. The E6B computer allows a pilot to literally draw a wind triangle, and he gets to visualize the relationship between airspeed, wind speed and direction, and where he's going. I know that you can just punch in a few numbers on a calculator and get the same results even more accurately, but you don't have the sense of what the wind is doing to the airplane. You don't think in terms of crab angles and drift angles as you do when using an E6B. I think the E6B is essential for learning the relationship between wind, track, and the airplane, what it's doing. I would like to think that the E6B has a lot of life left, but something tells me that it doesn't, simply because we're moving so rapidly into the computerized age that if it doesn't happen automatically, pilots are going to become impatient with it. I used to teach, and I still like to teach new students to actually draw wind triangles right on the chart and get a sense of what's happening, the relationship between wind and the aircraft. And the E6B helps to do that. But the calculator, it's so easy to stroke a wrong key and come up with the wrong information. And if you don't have a good sense of what to expect as an answer, you might rely on the wrong one.
Now let's take a look at an FAA test question and use this knowledge to work through a solution.
All right, back into the studio for a question on our final topic. We're going to ask you to refer to figures 21, 22, and 24, which the FAA will provide. What fuel would be consumed on the flight between Grand Junction, Colorado and Durango, Colorado, if the average fuel consumption is 15 gallons per hour, or GPH? All right, the answer is one of these three, but we have to go first to figure 21, which establishes our altitude of 15,000 feet. We go to figure 22, our flight log, and we check the flight log. The wind is given as 230 degrees at 8 knots. The course is given as 151 degrees magnetic. Convert it to true course by applying the magnetic variation 14 degrees to get a true course of 165 degrees. Now, the true airspeed for your aircraft, as shown here, is 175 knots. Enter the true airspeed into your flight computer and apply the wind correction. The result is a ground speed of 171 knots. Now, in figure 24, we find the time en route. The en route low altitude chart shows the leg from Herm intersection to Manka intersection is 75 nautical miles right there. Now, using our flight computer, we calculate the time for the second leg as 26 minutes and 20 seconds. The first leg and last leg are already provided for you in figure 22. The first leg is given as 24 minutes, and the last leg is given as 18 minutes and 30 seconds. By adding them together, the total time en route is 1 hour, 8 minutes, and 50 seconds. Now, find the total fuel burn. Using our flight computer, we set fuel burn at 15 gallons per hour. Calculate the total fuel burn for 1 hour and 9 minutes as 17.2 gallons. The answer, of course, is A, as most correct. The total fuel burn for 1 hour and 9 minutes is 17.2 gallons. Okay, that does it for lesson number 7. We'll tackle lesson 8, arrival procedures, next.